Why hello lovely humans, Jen Foxbot here. Welcome to another edition of Math Mondays, da 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 da, yeah. In this episode we are going to tackle how do we read these pesky math equations. What are we doing here? So I'm going to break this into at least two parts. In part one we're going to talk about the general way that we read math symbols with a focus on understanding that math really is just a language. It's a little bit different than written and spoken languages that we're used to, but it is a language. And in part two, we will look at how we use our understanding of math as a language to actually apply it, like as is done in science or engineering or computer programming. Okay, so just like English and Farsi and Mandarin, mathematics is just a language. In written and spoken language, we use symbols, which represent sounds, and together those sounds represent words. These words we give meaning to, and maybe those words represent a thing, a tangible object, like an animal or a tree or a pillow. These words can also represent concepts like love and imagination, things that we can't actually hold in our hands. Words, as we've gotten more sophisticated, we've also had to add more things that words can be. For example, internet. The internet wasn't a word 100 years ago, and so we've had to combine these sounds represented by symbols. Internet, how do I spell internet? I-N-T-E-R-N-E-T. We've combined new symbols as in letters to create new words that have different types of meaning. And so let's say I wanted to create a new language. Maybe I would start, it makes sense to start with new symbols. And so maybe I figure out a way to write symbols that haven't been done before, or something like that. But these symbols are just symbols. They don't have meaning until I give them meaning. One way to do that, which we might have done as a kid, where you're trying to write a secret code that adults can't understand, one thing that you might do is you and your friends get together and you either come up with words that are gibberish or symbols that are gibberish, quote unquote, and then you map them to an existing language. Since English is the only language that I am fluent in, I'm going to use English letters. So let's say if I wanted to give these symbols meaning, maybe I could say, okay, well, this equals A, B, C, and then I could write more symbols representing the rest of the letters, and then I can learn how to read, write, and speak my language. Maybe these symbols sound the same as English letters, maybe they don't. I can decide that, but I have to give these symbols meaning first. And then I can teach others so that we can talk in our secret code language. So math is the exact same way. It's a little bit different than written and spoken languages, but math is represented with numeric symbols, which represent quantities. So we have numeric symbols 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are just symbols. I have learned, as we all have, their names, which may be different in different languages. Although I believe most of the world, I shouldn't say that, but many of us use these digits as is, but we might have different names for them. Un, deux, trois, en français. At some point, eins, drei, zwei. I should be learning German because my nephew speaks German. Anyway, so we call them different things, but typically, at least if you speak a Western language, you'll be used to seeing these. Again, just symbols. They have no meaning until we ascribe them meaning. But these all represent quantities of things. The reason why we have 10 digits is because most humans have 10 fingers. If most of us only had 5 fingers, we would probably have a base 5 system. This is called a base 10 system, which is how we count things. We count things up to 10, and then that's like our unit, and then we count another 10, that's another unit. But if we only had 5, we might have units of 5. If we only had 2 fingers, then maybe we would count in a base 2 number system or a binary number system. So these symbols have meaning based on our, understanding of the world and the fact that we probably started counting on our fingers because they're pretty accessible. If I wanted to figure out how many apples I picked, I'd be like, well, let me just keep track on my hand. And actually, the first known written mathematics was due to accounting. I want to say it was keeping track of animals or crops or something like that. I can't remember. But basically, math has been a way using these symbols to represent quantities to keep track of certain amounts of things. Okay, so we have that down. Now we also have, in the language of math, we have symbols that represent operations, or the way that we combine different quantities. So we have things like addition and subtraction. We also have things like multiplication and division, which both of these are just faster and lazier ways of doing addition. So for example, 5 times 5 is another way of saying, let's add 5 times, or 5 plus 5, which is 10, plus 5, which is 15, plus 5, which is 20, plus 5, which is 25. So both of these equal 25. And that's why I say math is really about understanding the rules and the meaning rather than memorizing. You can sit and memorize multiplication tables and that'll allow you to do things faster, but we need to understand what this operation symbol is telling us. Pretty cool, right? And so just like I mentioned how as humans have discovered more about the world and have created new things, we have invented new words. We have also had to invent new operational symbols to allow us to do the kinds of calculations that we've needed to do to pursue our intellectual questions and things like that. So just as we have added, eventually we added a symbol multiplication so that we could be lazy and save paper or stone or whatever we were writing on, we have also had to add more symbols like the summation sign. So the summation sign, if I wanted to represent 5 times 5, I could do this, 5 subscript I with I equals 1 to 5. So we read this as saying, okay, we have a term here which is being added. The subscript tells us basically the index, or the, it allows us to keep track of the ith unit or the number of 5s that we have. Like if it was 5 subscript 1, that would be the first 5. And we add from I equals 1 until we get to I equals 5. Those of you who have done coding are really familiar with for loops and indices. This is the mathematical way to represent that. So this would be 5 subscript 1 because this is our first 5. This is 5 subscript 2 because this is our second 5. This is 5 subscript 3 because our third, 5 subscript 4, and 5 subscript 5 because that is our fifth 5. And so that just equals 25. This might seem a little bit trivial because is this faster than writing 5 times 5? No. But imagine you had, I don't know, like something a little bit longer here, or if you had a quantity in here that was actually changing depending on which index it was. Like for example, if your first index was 1, your second index was 2, your third index was 3, it would be a little bit different. So that might look something like, I don't know, we could do 1 over I, for example, where you replace I with the particular index. So the first index would be 1 over 1, plus 1 over 2, plus etc. So summation signs were invented because we needed to add a lot of things together and we wanted to be lazy. And eventually summation wasn't quite enough, and so we needed the integral sign. So the integral sign, which looks like a long stretched out S, is a way for us to add together quantities that are not discrete or things that are continuous. So it allows us to add together integers or whole numbers, fractions, and everything in between. So if we wanted to, again, represent our 5 times 5, what it would look like is this, where we have 5 dx. And we are going to add from 0 to 5. And I'm going to draw us a picture. Pictures are super helpful in mathematics, especially with integrals. So what this looks like is if our function, which is dependent on x, equals 5, that means that on the vertical axis we have f of x, or if you're more comfortable with y, that's fine too, but it always equals 5. So it's going to be a straight line, or yeah, it should be a straight line. So for any value of x, if x equals 1, f of x is 5. For x equals 2, f of x is always 5 for every value of x, whether it's x equals 1, x equals 2, x equals 1.5, x equals 1.25, our function always equals 5. And now what our integral is doing is it's saying, okay, well, I want to add up this function, everything under this function, from x equals 0, which is right here, all the way to x equals 5, which is going to be somewhere out here. So on the horizontal axis, I'm going to label that x because we're going to be good mathematicians. And so basically what we do is we add up all of these little teeny tiny amounts all the way up until x equals 5. And since this is continuous, meaning that it's every number between 0 and 5, what we're doing is we're saying, okay, what is the sum from x equals 0 to x equals 5 of this function? And so now we do have to call in our understanding of how the integral works. From intuition, you might say, okay, well, if I add up, if your understanding of area includes rectangles and things like that, then you'd say, okay, well, if we're just adding up the length of this to the, all the way to the length of this, well, then it's just 5 times 5 is 25. That's it. That's what an integral is doing. It is a sum under the curve. In this case, our curve is a flat line, so it's pretty straightforward. But we apply our understanding of the rules of integer, or the meaning of the integer symbol, and we get 5 times x from 0 to 5, which is going to be 5. We replace x with our final value and then minus our initial value, so that's going to be 5 times 5 minus 5 times 0 equals 25. Boom! So there you go. All of these symbols are just different ways to represent different ways of operating on numbers. And our numbers are quantities. As you get higher in mathematics, what you find, like we've done here, is that quantities can be represented by letters, which really just means that they are a placeholder. Oftentimes it means that that quantity can change. Maybe it changes over time, maybe it changes over distance. For example, we could use A to represent our age because our age is always changing, so it goes. But again, it's just symbols, and to really understand how to read mathematics, we have to understand what the symbols mean. Understanding the quantities is fairly straightforward, so really what it comes down to is understanding what these operational quantities mean and what the rules are. And just like learning any language, that requires practice. So in part 2, we are going to dive into what it means to apply science or some other application to a mathematics equation, because that will actually change how we read it a little bit. If you have any questions about what we covered in this part, or if you're wanting to learn more about what a particular symbol in math means, let me know. Leave a comment. Cool. All right, so I'll see you for part 2. Yeah!